I will now talk about an example that's slightly different from the ones we've seen before. We have seen the weighted compatible intervals, longest increasing subsequence, both of which basically work in arrays or sequences of numbers. And we have seen the all pairs shortest path, which works on graphs. I want to now talk about a problem that works on two strings or two sequences of letters. This problem has deep motivation in biology. I'm not going to talk about that, but if anyone is interested, you can look up the problem of pairwise sequence alignment, which is again given two biological sequences, let's say one from human, one from chimpanzee. You want to basically align and see what happened to them as they evolved from a common ancestor. That's known as the pairwise sequence alignment. I will be talking now about a very similar problem. Actually, the dynamic programming or the recursive function is the same between the two, but I will talk about it a little bit simplified, and we will look at it as basically thinking about strings here. Okay, the problem I talk about is known as the longest common subsequence. The longest common subsequence problem. Okay, and let me actually show it through an example. Suppose I give you two strings, okay, x and y, and x is this is a book. Okay, this is just one string that has this is a book, one word, and y is the book. Okay, imagine I give you these, and I ask you, can you find me the longest common subsequence? Not substring. Substring is that a substring is a set of letters that are contiguous. Okay, so this is a substring. Book is a substring. But if I'm talking about subsequence, for example, I can take SSB is a subsequence. I can take SSB as long as I take them in the same order. BSS is not a subsequence because this is not respecting the order. Okay, so if I give you these x and y, I ask you what is the longest common subsequence from this. Well, if you look at this, actually I give an easy example so that we can find it easily here. If you look at this here, if you take th book and th book, so thbok, it's a subsequence of x, it's a subsequence of y, so it is common subsequence of the two, and it is the longest possible. You cannot find any other subsequence that is common to both of them and longer than this one. Okay, so this is the problem here, that we are going to be given. We are going to be given x is x1, x2. These are the letters of x from x1 to xn, and the letters of y, y1, y2 to ym. They don't have to be of the same length, and we want to find the longest common subsequence. I'm not going to be writing pseudocode here. I'm not going to be showing the traceback of how to find the longest common subsequence. I want to talk about the recursive reasoning and what is that, the formula, and how do we implement it in terms of storing values so that we avoid solving overlapping subproblems multiple times. Okay, so the way we think about this is as follows. So imagine that we define, again, I will first talk about it in terms of functions, okay, the functions that we can call recursively. So imagine that I define opt for optimal, again, opt of ij. It's the length of longest common subsequence of x1, xi, and y1, yj. Okay, so I'm going to be looking now at the subsequence only of prefix of the first I letters from x and the prefix of the first j letters from y, and I want to be looking at the length of the longest common subsequence from this. So for example, if I look for these two strings here at opt, let's say 3, 4, I'm saying what is the length of the longest subsequence of the first three letters from X, THI, and THEB from this one. It will be 2, okay? Because the length of the longest subsequence of the first three letters from X and the first four letters from B is just TH, which is 2 letters, okay? And now we need to reason about them here, and let's look at this. X1, X2, all the way to Xi, Y1, Y2, all the way to Yj. Now, we cannot talk about one letter at a time. We have to talk about a letter from X and a letter from Y, right? So because we are looking for subsequence, it has to be something that's present in both. So imagine that what situation do we have here? We have a situation where we have xi equals yj, and they are part of the solution. If xi equal yj, they are the same letter, then I need now to look at an optimal solution from x1 to xi minus 1 and y1 to yj minus 1. So this will be opt of I minus 1, j minus 1. And since we have already one letter that is common to both of them, which is xi and yj, which is the same letter, this will be 1. So this is if xi and yj are going to be taken as a common letter, and we're going to append that to a longest common subsequence of the first I minus 1 letters in X and the first j minus 1 letters in Y. A second solution is that we know xi is not going to be part of a solution. So xi and yj are part of the solution. And second case is xi is not part of the solution. It's not part of a longest common subsequence. So I need to get rid of xi. So now I'm looking for a solution. If xi is not part of a solution, then I need to look at x1 all the way to xi minus 1 and yi to yj, right? Because xi is not part of the solution, but still yj could be part of a solution. So this one now, I am looking for opt of I minus 1 j. The third option is that the I minus 1 is not part of the solution. If the yj is not part of the solution, then our problem now becomes x1, x2 all the way to xi, but y1 to yj minus 1, in the sense that I can ignore yj. Okay, so here in this case, it is opt of I, j minus 1. Okay. Now, there are mutually exclusive cases here, right? So if I take this here, this is one possibility, that we have that opt of ij is 1 because xi and yj are the same letter, and then I can say opt of I minus 1 j minus 1. And the second option is, even I and j might not be the same letter, but even if I and j are the same letter, doesn't mean I have to consider them together as part of the solution, because I could have used yj to align it, to match it to some other letters in X. So opt of ij, now we need to look at the maximum of either this is, so if this is here, if I equal j, in fact we can force them. If I apologize. If xi equals yj, we can actually always force them to go together, okay? Even if they don't have to go together, if yi went with xi minus 1, that's fine. I can actually, if yj went with xi minus 1, I can replace that by yj goes with xi without losing anything, okay? So I can take opt of ij to be 1 plus opt of I minus 1 j minus 1 if xi and yj are the same letter. If xi is not the same as yj, then either xi might go with all the other, with some of the letters from 1 to j, or yj will go with one of the letters from x1 to I minus 1. And this is where the opt I minus 1j or the opt of ij minus 1. And we take this max. Now, of course, if I is 0 or j is 0, then opt of ij is 0. The length of longest common subsequence between two strings, one of which has no letters in it, has to be 0. Okay? So this is the recursive formula here. We look at, forget about that the case of 0, but we look at the letters xi and yj. And if they are the same, let's put them in the solution together. If they are not the same, let's see if xi works with something other than yj, but something before yj, or if yj goes with something before xi. Okay, and these are the opt I minus 1j or the opt ij minus 1. And this is, if opt is the name of a function and you call it like this is going to be a recursive function, exponential running time if this implementation, but you can actually turn it into a table. So instead of opt being a function, you can actually turn it into a table. Aij, again, equal 0 if I0 or j equals 0, or I minus 1, j minus 1 plus 1 if xi equal yj, or the max of I minus 1 j and the ij minus 1 if xi is not equal to yj. And at the end, what we want the algorithm to return is ANM, right? Because n is the length of x, m is the length of y. And this algorithm here, if you write it in this dynamic programming fashion, it is an O of n squared algorithm because we are filling an n by m. For n and m, it's O of n times m, because we are filling a matrix of n rows. So we can have the x here and the y here, and this is A, and ij would be here. And at every point here, we are looking at one of three values. If you want to look at I minus 1j, it's this entry. If you want to look at aij minus 1, it's this entry. If you want to look at ai minus 1, j minus 1, it's this entry here. And each one of them, it's O of 1 to look up these values. So this would be an algorithm for the longest common subsequence. Again, here we are dealing with two sequences or two strings at the same time. This is why we need to be looking at the two strings simultaneously, okay? And this algorithm is O of n squared, and the solution is here. This is the value. This is the length of the longest common subsequence. And to find the actual common subsequence, if we want, we do trace back in this matrix, again, based on this formula here. Did we come to A of mn from A of m minus 1, n minus 1? If that's the case, then you go this way, and otherwise you go in the other directions, okay? I highly recommend that you write the pseudocode for both filling this matrix and getting the value of A of nm, and doing the trace back to get the actual longest common subsequence, okay?